Hey Royals, in our last video, we investigated the magnetic field around a long, straight conductive wire. And what we're going to do is we're going to now take that piece of wire and we're going to form loops with it. So imagine I have a single piece of wire and I make just one single loop here. And as my current comes into this loop, let's assume that it is traveling in this direction. So as it comes, and let's adjust the point where it cuts kind of this plane, we have the current going in on the right-hand side of the loop. Now, if we follow it around and it comes to the other side of the loop, we have that the current is coming out of the page. So I have a simulation here that will simulate what's going to happen to our magnetic field lines in the region in between the two wires and on the region outside of those two wires.
So let's look at what happens when we have current running through wires and they're not acting in the same direction. So first of all, if I had a wire that was running into the page here, and we're going to have blue indicating into the page and red indicating out of the page. If I have a blue wire, so this is going into the page, applying my right hand rule for a straight wire, my thumb would be pointing into the page right now or into your screen, and you'll notice that your fingers wrap around in a clockwise fashion, right? So if I did that on the left hand side, and let's remove this one here, and we insert same situation, it's going into the page, but now it's on the right side. You'll notice again, it's a clockwise manner for the magnetic field around these two. Now, I want you to pause the video and think about what would happen if I had two wires that were running directly into the page here. So on the left-hand side, I have a wire that's going in, and on the right-hand side, I have a wire that's going in. So you might notice that you have some of your fields canceling each other or adding to zero. So let's actually introduce that and figure out what's actually happening here. So you can notice the charge on our right-hand side here has our clockwise rotation of the magnetic field. And on the left wire, we have the same clockwise rotation. So if we think about what's happening when we come to the middle here, on the left wire, we have the magnetic field acting downwards. And on the right wire, we have the magnetic field acting upwards. So the upwards vector and the downwards vector would add to have a magnitude of 0. So you'll notice that if you have wires that are running in the same direction, they're parallel to each other, the magnetic field directly halfway between them will sum to 0. So now let's look at what happens if, say, my wires are running in opposite directions. So I'm going to introduce our wire again, going into the page on the left-hand side. But before we do that, I want to bring up the wire that's going out of the page. Now, using our right-hand rule, we have our thumb pointing out of the page, and our fingers will now go in a counterclockwise rotation. So now again, if I have this set up, so with the counterclockwise rotation of the magnetic field and the clockwise rotation of the magnetic field, I want you to pause the video and think about what would happen directly between these two. So hopefully you came up with the fact that the vectors would add, and it would actually strengthen the magnetic field between the two. So if we were to introduce that second wire now, so I have a wire going into the page and a wire coming out of the page, I notice that these vectors that are coming downwards on the right-hand wire add with the wire that is going into the page. And notice that there's a region in between here that has a lot of vectors that are pointing straight downwards. So the magnetic field actually gets stronger when we have wires that are running in opposite directions. So let's go back and actually apply this to the idea of a coil.
So you could see from that simulation that the magnetic field lines caused by the wire going into the page wrapped around the wire in a counterclockwise manner. And the wire that was coming out of the page had the field lines oriented so that they would go counterclockwise. And this increased the magnitude of the magnetic field in between those two pieces of wire. So we had in the region between them a strong magnetic field, and then on the regions on the outside, the magnetic field became much weaker. So one way that we can actually increase the magnetic field strength is to loop our wire several times over and over and over on itself. So that's what we have here on the right-hand side of this page. So if we look at this situation, this is our positive terminal of our battery. And we know that due to conventional current, the current is going to come out of that end of the battery, and it's going to go up into my coil. So as it goes up around the back of my coil, it's going to be coming down on the front, and it's going to be going up on the back. So my current right now is actually coming down on the front of this coil. So at the very top, my fingers will be coming out of the page, and at the very bottom of the diagram, my fingers are going into the page. Okay, so let's investigate how this single loop can be turned into multi-loops. Now, if I take a slice of just the top of the coil, I get this region here. So I have 1, 2, 3, 4 wires that are coming straight out of the page on us. And if I look at the bottom of our coil, we have 4 wires that are going into the page. Now, if we use our right-hand rule for the straight wires, we can see that the magnetic field around this wire in the top of our coil will be going counterclockwise. So each of these wires will cause a counterclockwise magnetic field. Similarly, the magnetic fields on the bottom of the coil would be going clockwise, and each individual wire will create its own magnetic field. So what happens in the region in between? So if we think about each wire has to form its own magnetic field lines, that's going to cause the field lines to get more concentrated in the region in between our coils. So on the inside of the coil, you're going to have that the field strength increases because the magnetic field lines can't touch. So I've actually drawn one that touches, and we don't want to have that. So my magnetic field lines cannot touch. And so since they actually essentially repel each other, they're going to compact themselves in the area in between the coil. Now, when they come on the outside of the coil, there's much more space for them to form, and the field becomes much weaker. Now, if you think about what this actually looks like, we have field lines all coming out of one end of the coil, and they're all going into the other end of the coil. This looks very similar to the magnetic field lines around a bar magnet. So a coil, in fact, actually produces, when current's going through it, it produces a semi-bar magnet. So it has a north acting pole and a south acting pole. So that supports the fact that even more that a coil of wire with current going through it acts similarly to our bar magnets. Now, there's a right-hand rule that will help us out with this. So the right-hand rule will actually tell you what end of the coil acts like the north pole on our bar magnet. So how we do that, we're going to grab the coil with our right hand and point our fingers in the direction of the current. So now with our coil that we had before, I've just drawn another picture of it at the bottom here. Our current is actually acting down on the front. So I have to actually grab it so that my fingers come down on the very front of my coil, and my thumb will be pointing towards the right. So that is how we will determine what end of the coil acts like that north pole. So how can I actually increase the magnetic field? Well, there's 4 ways that I can actually do this, and all of them will increase the force that the magnetic field can apply. Since the strength of the magnetic field is related to the amount of force that it can actually apply, we're just going to talk about how the magnetic field can increase, and that would mean how does the force increase as well. Okay, so the first thing I might be able to do is increase the current going through the wire. And as we saw in our straight wire investigation, we saw that as we increased the current, the magnetic field strength actually increased as well. And it was linear. So that means that they are direct variations. If one goes up, the other one goes up by the same amount. The second way that I can actually increase the strength of the magnetic field is just to increase the number of loops. So the number of times that I actually wrap my wire around and around and around will increase the strength of the magnetic field. So if I use a 9-volt battery and I create just a single loop of wire on it, I use a device that can measure the magnetic field. With one loop, it creates a magnetic field strength of about 5.06. So if I increase it to be 2 loops, you'll notice that it has actually just double the single amount. So if I increase one more time, it should increase by about 5.06. And there it goes again. And one more time, you'll notice that it increases by the same amount. So what does that mean? That means that the number of loops is linearly dependent on the strength of the magnetic field. Another way that I might be able to do it is I can change the cross-sectional area of the inside of my core of my coil. So if I think about this as my cross-sectional area, if I were to have, say, 3 field lines that were able to fit between it, that would be the strength of my magnetic field. Now, if I just decrease the area in which those field lines can actually go within, the field lines have to get a lot closer to each other. And we know that when field lines are closer, they actually increase the magnetic field strength. Okay, so that's another way that we can actually increase the magnetic field strength. It's just make the coil smaller. And when I mean smaller, I mean that the circumference of it is tighter. Okay, the last way that I can do it is actually to stick something inside the core of my coil. So if I think about this coil right now, it looks like there is a solid cylinder of some sort inside that coil. So it's something that I wrap my wire around. Now, air would have a permeability of 1. Permeability just means the ability to be magnetized. So air has a permeability of 1, but if I put iron inside that coil, inside the core of my coil, it will increase the magnetic field strength. And that's because iron has all these domains that we investigated, and they will align and amplify how strong that magnetic field is. Okay, so if we're looking at how this all relates, we can actually put it together with an equation. And my equation here is wrong. These should actually be multiplications, and they should be right on your page. So that means that the strength of the force that this magnetic field can apply is related to the current, the number of loops, the cross-sectional area, and the permeability of the core. Okay, so I have a sample problem here for us to try out. The sample problem has a solenoid. It has a core that has a permeability of 1 because it's air. So air has a permeability factor of 1. That's what we use as kind of our base or our reference point when we're talking about permeability. So anything that has a larger permeability than 1 has a better permeability than just simply air. So if you had something on the order of 2 times 10 to the 5, which is the case if we inserted a piece of metal into the core here, it would actually increase the strength of the magnetic field because each of those small domains will align itself with the magnetic field and increase or strengthen the magnetic field itself. Okay, so if we look at this situation, I know that the force that this original coil is able to exert is 0.010 newtons. I have that in the 2 situations, I don't increase the number of turns or loops. It stays as 1.0 times 10 to the 2. My current goes from having a value of 5.0 amps to having a current of 25 amperes. And that my permeability initially is 1 because we have it as air. And the permeability after I put this piece of metal into my coil becomes 2 times 10 to the 5. Okay, so if we use that equation that we had at the top of the page here, we have that F2 divided by F1, the ratio of the 2 forces, is equal to the ratio of the currents. So hang on here, 2 divided by 1 multiplied by N2 divided by N1 times A1 divided by A2. Remember, it's inverted there because of the fact that the magnetic field is inversely proportional to the area, multiplied by the permeability of 2 divided by the permeability of 1. And I'm looking for F1 here. Okay, so if we were to substitute in all our values, we get F2 divided by 0.010 is equal to 25 divided by 5 times 1 times 10 to the 2 divided by 1 times 10 to the 2 times 1 divided by 1 for my areas times 2.00 times 10 to the 5 divided by 1. And you can rearrange this and find out that the force that this new coil could exert would be 1.0 times 10 to the 4 newtons. Okay, so this introduced us to the second right-hand rule, and we also looked at how we could actually increase the magnetic field within a coil by just changing the geometry of the coil or how we made it up.